Hey guys, so someone requested me to solve this problem, so let's get on to it. Uh, in this problem, you have a frictionless pulley, which is the shape of a uniform solid disc. The mass of the disc is 2.5 kilograms, the radius is 20 centimeters. So this is a uniform solid disc with mass 20 kilograms and radius 20 centimeters. Now, a 1.5 kilogram stone is attached, and there is a string that is attached to the stone and that wraps around the pulley. Okay. Now the system is released, right? Gravity acts straight down. So when the system is released, the mass falls down and it gains kinetic energy. So as it falls down, the pulley will rotate fast and it will the rotation will increase. Now you have to find how far this stone should fall, right? So that the pulley has this kinetic energy, 4.5 joules. Okay, so you're looking for the kinetic, you're looking for the height, right? Through which the stone falls, and the pulley has kinetic energy for 4.5 joules. So this is rotational motion, right? This is rotational motion. This is translation. The motion of the stone is linear motion. The motion of the pulley is rotational motion. Okay, and in part B, you have to find the percentage of total kinetic energy. What percentage of the total kinetic energy does the pulley have? Okay. Now let's solve the system. There's just a toy model of what's going on, right? So you have a pulley, and then the mass is attached, and gravity points down. So as the mass falls, the pulley rotates, the string starts unwrapping, and the kinetic energy of the pulley increases. So okay. So let's write down what is given in the question. So we know that the rotational kinetic energy of the pulley should be 4.5 joules. Okay, we're looking for the height, which gives us this kinetic energy. The question says that the system is released from rest. So initial angular velocity is 0. The mass of the pulley is given. .5 kilograms, and the radius of the pulley is 0.2 meters, and the hanging mass is 1.5 kilograms. Okay, so the first thing to do is we can calculate the moment of inertia. This is usually the equation in these type of questions. The equation for the moment of inertia is given. In this question it's not, but when it's stated in an exam or a quiz, you will be given this equation, right? So for a uniform solid disc, the moment of inertia is always half mr squared. So if you plug in these numbers, mp equals 2.5 kilograms and radius equal, sorry, I'm using capital R, so let's use capital R. So radius equals 0.2 meters, you will get 0.05 kilogram meter squared. So we've got the moment of inertia of the pulley. Now the next thing to do is we need to use conservation. So since we need to find the height, right? The first thing in these question that you should always remember is that energy is conserved. As long as there's no friction involved, energy is conserved, right? So there are multiple methods involved to solve these questions based on what you know. So let's draw the picture so that you can see the forces. So here's the stone, there's tension over here, there's gravity over here, and tension over here. Tension is the reason the pulley is rotating, right? So tension provides the torque. So when the mass falls a height, let's say h, right, and when it falls through this height, the kinetic energy of the pulley will be 4.5 joules. So energy is conserved energy. This is our zero potential energy line, right? We can take that anywhere we want. So we're assuming that this is zero potential energy. So mgh, it has potential energy over here. When it reaches over here, the mgh is converted into the translational, right, kinetic energy of the stone, and the rotational kinetic energy of the pulley. So you get half mv squared plus half I omega squared, right? Now you can see that we know the moment of inertia, right? We know, no, this is the hanging mass. Okay, this is also the hanging mass. So we know the mass. We have to find this, but you can see that we don't know this, right? So we need to find omega, right? This is omega, the angular velocity, okay? And remember that v is related with r, v equals r omega, right? V equals r omega. So if we know omega, we can plug in for v also. So let's see how can we find omega. Now the rotational kinetic energy of the pulley is given, right? So k rotational, remember, is half I omega squared. Okay. Now we know k rotational is 4.5 joules, so we can, and we know the moment of inertia of the pulley, so we can get omega over here, right? So omega is equal to 2 times k rotational divided by I, square root of that. So that will give you the, if you plug in the numbers, you will get 13.4 radians per second. So this is the angular velocity of the pulley. Now remember this velocity, right? This is the tangential velocity. So this is also the velocity of this mass when it reaches this point. Okay. It is also the tangential velocity of the pulley. So this is also the tangential velocity of the pulley. Okay. So that's why it's v equals r omega. Okay. This is the velocity of the mass, and we plugged it equal to v equals r omega. So we've got this number now. Now we can go back to this equation, the conservation of energy, which is going to give us this height that we want. Okay. Now you can solve for the height. Okay. So let's solve this equation. You can divide both sides by mh times g. So if we plug in v equals r omega over here, since we know we know omega, so let's write it in terms of that. So h will be equal to half mh r squared omega squared plus I omega squared divided by mh times g. Okay. So that's your equation. Now if you plug in the numbers, you'll get 0.67 meters. Okay. So make sure you double check when you plug in the numbers. We know all these quantities. We know that mh is 1.5 kilograms, and so mh is 1.5 kilograms, moment of inertia is 0.05, omega we calculated is 13.4 radians per second. So we know all these numbers in summary, right? So you can get the height. So this is how you get the height, okay, through which the mass falls, so that the pulley has the 4.5 joules of rotational kinetic energy. Okay, good. So the next part of the question, where did that question go? Yeah, so the next part of the question is what percentage of total kinetic energy does the pulley have? So in order to find the percentage, what you can do is you can calculate the ratio of the rotational kinetic energy the pulley has and the total kinetic energy. Okay, So the rotated kinetic energy is given 4.5 joules. Okay, and the total kinetic energy is just mgh, right? Remember the total kinetic energy is the sum of the energies, right? So when the mass starts, right, it has some potential energy, right? All that potential energy is converted into the total kinetic energy that we have, the rotational plus translation. So mgh, when you calculate mgh, the total kinetic energy turns out to be 9.85 joules, and which is this is just mgh. Okay, you can plug in the numbers to check. Okay, total. Now, when you plug in that, you get 9.85 joules, and that is 40. Now, since you want the percentage, you want to multiply this with 100 and then percent, right? Multiply with 100%. Okay, so that gives you 45.7%. So that's your other answer. So this is what you wanted. You wanted the height and the percentage kinetic energy in part B. Okay, so this was problem 9.47. Okay, and if you have any questions, post them in the comments. Hope you like the video.